Yeah, good afternoon students. In the last session we have discussed about different types of differential configurations, AC analysis, DC analysis, right? Input resistance, output resistance and all these things. So now we will give the brief description about different types of differential configurations. See here, so we are having four types of differential configurations: dual input balanced output, dual input unbalanced output, single input balanced output, and single input unbalanced output differential amplifiers, right? If the output is taken between two collectors, that is called balanced output differential amplifier. If the differential amplifier contains one input, then we can say that it is a single input differential amplifier. If the output is taken between one collector and ground, then it is called unbalanced output differential amplifier. If you are having two inputs, then it is called a dual input unbalanced output differential amplifiers. So when it comes to DC analysis of the differential amplifier, so apply KVL to the base emitter loop. So then you will get this equation: minus IBRS minus VBE minus 2IERE plus VE equal to 0, and we know IC equal to beta IB. So substitute IB equation in the equation 1. Then you will get emitter current equal to VE minus VBE by RS by beta minus 2RE. Here beta value is large, so we can neglect the RS by beta ratio, right? So then IE becomes VE minus VBE by 2RE. So DC analysis means we have to calculate collector current and collector to emitter voltage, VCE. So here the collector voltage of Q1 is VC, so that is equal to VCC minus ICRC. So collector voltage means, so this voltage, if you subtract the voltage drop across resistor RC1 from VCC, then you will get the collector voltage. So VC equal to VCC minus ICRC. So and VCE equal to VC minus VE. So here VCE equal to VCC plus VBE minus ICRC. So it is the collector to emitter voltage. So these are the operating point coordinates. IC and VCE are the operating point coordinates. So in the DC analysis, we need to calculate these two values, IC and VCE. That is IC Q equal to IE, VCE Q equal to VCE. So Q means Q point or quiescent point that comes in DC analysis. So when it comes to AC analysis, here we need to calculate the differential gain, common mode gain, input resistance, output resistance. So apply KVL to these two loops. So it is the equivalent circuit of the differential amplifier. So apply KVL to two input loops, then you will get these two equations. So if you solve these two equations, and finally you will get IE1, IE2. So in the same way, V0 equal to VC2 minus VC1. So from this you will get RC into IE1 minus IE2. So substitute IE1 and IE2 in the equation, then finally you will get the differential gain. The differential gain of the differential amplifier, right? So it is the input resistance. Next one is the input resistance. It is the ratio of input voltage to input current. So V1 by IB1, and V2 equal to 0. So for this you will get, it is beta RE dash. So we are using two emitter resistors, so that's why the input resistance becomes 2 beta Re dash. 2 beta Re dash. That is the input resistance. So when it comes to output resistance, it is defined as the equivalent resistance measured at one output terminal with respect to ground. So R01 equal to R02 equal to RC. The collector resistor is the output resistance of the differential amplifier. So these are the important formulas. So in the DC analysis, we are going to calculate IC and VC values. In the AC analysis, we are calculating the differential gain, input resistance, output resistance. Okay, so these are the comparison table of the different types of differential amplifiers. So for the balanced output, the differential gain is RC by RE. For the unbalanced output, the differential gain is RC by 2RE. So and input resistance is 2RE beta AC. So input resistance is common for all differential amplifiers, and the output resistance is also common for all differential amplifiers. Okay. Up to this we have discussed in the last class. Today we will see how to improve the CMRR. So how to improve the CMRR. What is CMRR? So CMRR is the ratio of differential gain to common mode gain. So here CMRR equal to AD by AC. So CMRR means how effectively the noise can be eliminated. The noise can be eliminated in the differential amplifier. That is identified by the CMRR, common mode rejection ratio. How effectively the noise can be eliminated in the differential amplifier is identified by the CMRR, common mode rejection ratio. So CMRR is the ratio of AD to AC, AD by AC. So to maintain high CMRR, AC must be low. To maintain high CMRR, AC must be low. So the ideal value of CMRR is infinity. So generally, for operational amplifiers, the CMRR must be high. The CMRR must be high. If CMRR is high, you can say that the noise will be low. Here the common mode signal is nothing but noise. The noise will be low. So to maintain high CMRR, here the AC value must be low. And we have the relation AC is directly proportional to 1 by RE. So AC should be low. So AC is directly proportional to 1 by RE. So here RE should be maximum. To maintain AC low value, RE should be maximum. So if RE maximum, then we have the following drawbacks. That is, chip area will increase. We have some drawbacks if RE is maximum. If you choose RE maximum value, we have some drawbacks. That is, chip area increases and cost increases and the power consumption also increases. So these are the drawbacks when you select maximum RE value. So chip area will increase, cost increases, and the power consumption also increases. So that's why RE should not be maximum, right? So to eliminate these drawbacks, we are using constant current source method and current mirror circuit. We are using two methods. To maintain high CMRR, here we are using two methods. So constant current source method and current mirror circuit. See here, what is current mirror circuit? So it is one of the important topic, current mirror circuit. So current mirror, what is the purpose of current mirror circuit? The current mirror circuit is used to improve the CMRR. To improve the CMRR. So what is current mirror? As the name implies, current mirror, right? So here the output current is equal to the input current. In the current mirror circuit, the output current is equal to the input current, right? So the circuit in which the output current is forced to equal the input current is said to be a current mirror circuit. As the name implies, mirror, right? So here the output current is forced to equal the input current. So that is the function of the current mirror circuit. That means the output current is a mirror image of the input current. So both are same. Output current and input currents are same. The output current is a mirror image of the input current. So here see the derivation. Here we are having two CE mode transistors. So Q3 and Q4. This is the current mirror circuit. So Q4 base is connected to Q3 base. Q4 base is connected to Q3 base, and two emitter resistors, Q3 and Q4 emitter resistors are combined. Right? Here the output current is IC and the input current is IC and the input current is I2. Okay? Output current is IC and the input current is I2. So it is a R2 ratio, right? See here, for Q3 the voltage between base and emitter is VBE3 for Q3. So these two transistors must have the same characteristics. These two transistors must have the same characteristics. Then only the output current will be equal to the input current. So here the VBE3, it is the voltage between base and emitter of Q3 transistor, and VBE4, so it is the voltage between base and emitter of transistor Q4. So these two currents will be equal. VBE3 equal to VBE4. The transistors are having the same characteristics and the two transistors are of same type. So then we can write VBE3 equal to VBE4 and IB3 equal to IB4. So two base currents, IB3 equal to IB4 and IC3 equal to IC4, right? So these two currents are equal and VB3, VB4 are equal. So here IB3 equal to IB4, IC3 equal to IC4. At node VB3, see here, at node VB3, the current divides into here at VB3 or see at this node. So I2 is divided into two currents. Here I2 is divided into two currents, that is I plus IC4. I2 is divided into two currents, I plus IC4. So I2 equal to IC4 plus I. So we can write I2 equal to, at this node, I2 equal to IC4 plus I. So this we can write I equal to, again I is divided into, at this node I is divided into two currents, IB3 and IB4. IB3 and IB4. So at this node I2 is divided into two currents, IC4 and I. At this node I is divided into two currents, IB3 and IB4. So here IB3 equal to IB4, so we can write 2 IB4 or 2 IB3, right? So I2 equal to IC4 plus 2 IB4, that is equal to IC3 plus 2 IB3. Why? Because these two currents are equal, IC3 equal to IC4 and IB3 equal to IB4, right? So here I2 equal to IC3 plus 2 into, in place of, so 2 into IC3 by beta. So in place of IB we can write IC by beta. So it is IC3 by beta, right? So take IC3 is common. So IC3 into 1 plus 2 by beta DC, right? So here 2 by beta DC value is small because beta changes from So 50 to 500. So that's why this ratio will be low. So we can write I2 equal to IC3. We can write I2 equal to IC3. So here I2 is the input current and IC3 is the output current. Okay. So output current, that is IC3, is the mirror image of the input current I2. So that is the concept of current mirror circuit. So current mirror is used to improve the CMRR value. To improve the CMRR value, we are using this current mirror circuit in the differential amplifiers, so in the operational amplifiers. Okay. Output current is equal to the input current. So that is the current mirror circuit. So next, see here, it is a cascaded differential amplifier. It is a cascaded differential amplifier. So you know what is cascading and what are the advantages of cascade amplifiers? So cascading means the output of first stage is connected as a input to the second stage. The output of first stage is connected as a input to the next stage, right? So the output of second stage is connected as input to the third stage, like that. So this type of connection is called as cascading connection. See here, it is a cascaded differential amplifiers. Cascaded differential amplifiers. Cascading means the output of one stage is given to the input of another stage. So cascading provides large amount of gain. The main purpose of cascading connection is to improve the gain. So to get the higher gains, we are using cascading connections. So this differential amplifier consists of two stages. First stage is a dual input balanced output. So this stage, it is the first stage. This stage is a dual input balanced output. So here we are having two inputs. So that's why it is a dual input. It is called dual input. And output is taken between two collectors. See here, the output is taken between two collectors. So that's why it's called dual input balanced output differential amplifier. Right? The second stage, see here, this connection is connected to, it is applied to the base of Q4. Here it is applied to the, this output is applied to the base of Q3. Right? So the output of first stage is connected to the input of next stage. The output of first stage is connected as an input to the next stage. So that's why this type of connection is called as cascading connection. Right? So this first differential amplifier is dual input balanced output differential amplifier. So why? Because here the output is taken between two collectors. Okay, Q1 and Q2 collectors. So that output is applied to the bases of two bases of next stage transistors. So when it comes to second stage, so it is a dual input unbalanced output. So second stage is a dual input unbalanced output differential amplifier. See here, the output is taken at one collector, right, with respect to ground. So the output is taken at one collector. That's why the second stage is a dual input unbalanced output differential amplifier. So to get higher gains, we are using the cascaded differential amplifiers. See here, the resistors of RC1, RC2 are same, and the resistors of RC3 and RC4 are same, and the two emitter resistors are combined, that is 4.7 kilo ohm resistor. Here the two emitter resistors are combined, and it is a 15 kilo ohm resistor, right? So it is a cascaded differential amplifier. Cascaded differential amplifier. So next, see here, it is a FET differential amplifier. FET differential amplifier. So almost the concept is same. So to form a differential amplifier, we require two transistors. Here in the FET differential amplifier, we require two field effect transistors. So two collector resistors, right? Two emitter resistors. Everything is same. But in FET differential amplifier, so we are using the two field effect transistors. Why we are using this FET differential amplifier. So to improve the input impedance, we are using FET differential amplifiers. So it produces the input impedance in the order of mega ohms, right? So the basic difference between BJT and FET is the FET has high input impedance compared to BJT. FET has high input impedance compared to BJT. So if you take the differences between BJT and FET, BJT has high gain compared to FET, but the FET has high input impedance compared to BJT. So to get higher input impedances in terms of mega ohms, we are using FET differential amplifier. So it is a junction field effect transistors. So JFET dual input balanced output differential amplifier. It is a JFET dual input balanced output differential amplifier. So simply in BJT we are having VCC here, but it is VDD. So gate, source, drain. The terminals of FET are gate, source and drain. So the power supply applied to drain, it is the VDD, right? So this resistor is gate resistor. Okay. So it is the drain resistor. So in BJT we are having RC, but whereas in FET we are having RD. So in BJT it is RB, so base resistor, but here this resistor is RG, gate resistor, right? So it is about FET differential amplifiers. To get higher, to improve the input impedance, to get higher input impedances, we are using FET differential amplifiers. So next, the important concept is level translator. Level translator. See here, what is a level translator? What is the necessity of this circuit? One second. So in the multi-stage amplifiers, we are having three types, that is RC coupled amplifiers, transformer coupled amplifiers and direct coupled amplifiers, right? So in the RC coupled amplifier, we are using resistors and capacitors to couple the two stages. Okay, in the RC coupled amplifier, in the two-stage RC coupled amplifier, we are using the capacitor to couple the two stages. In transformer coupled amplifier, we are using the transformer to couple the two stages. Okay, so in direct coupled amplifier, directly we are connecting the output of first stage is connected to the input of second stage, right? That is in direct coupled amplifier. So the main purpose of level translator is the DC level of the first stage should not enter into the second stage. The DC level of the first stage should not enter into the second stage. If the DC level of the first stage is entered into the second stage, then the biasing conditions of the second stage will change. That is the main drawback. If the DC level of the first stage is entered into the second stage, the biasing conditions of the second stage will change, right? So in RC coupled amplifier and transformer coupled amplifier, to couple the two stages, we are using capacitors and transformers. But in the operational amplifiers, to reduce the DC level, we are using level translator circuit. To reduce the DC level, we are using level translator circuit. See here, it is a level translator circuit, it is a simple level translator circuit. So because of the direct coupling, the DC level at the emitter rises from stage to stage. This increase in DC level tends to shift the operating point of the succeeding stages and therefore limits the output voltage swing and may even distort the output signal. Okay, so to minimize the DC level or to shift the output DC level to 0, the level translator circuit is used. Okay, so that is the function of the level translator. So level translator circuit, it shifts the DC level to 0 level. Okay, if the DC level is entered into second stage, the biasing conditions of the second stage will change. That is the drawback. So that's why to shift the output DC level to 0 level, the level translator circuits are used. So it is emitter follower. This circuit, it is a emitter follower with voltage divider is a simplest form of level translator circuit. So emitter, why it is called emitter follower? So this circuit is called as emitter follower with voltage divider is the simplest form, right? So it is a emitter follower circuit. Why it is called emitter follower means the output is taken at emitter. The output is taken at emitter terminal. So that's why it is a emitter follower circuit. Here the voltage is divided between these two, right? So that's why it is called emitter follower with voltage divider circuit. That is a function of the level translator circuit. Okay. So now we will see what is the integrated circuit. So operational amplifier, it is an integrated circuit, op-amp. So it performs different types of operations like addition, subtraction, multiplication, integration, differentiation, log, anti-log, all these functions performed by the op-amp. So it is a IC, integrated circuit. What is the integrated circuit? Integrated circuit consists of active and passive components. Active and passive components. So fabricated together on a single crystal of silicon. So it consists of resistors, capacitors, transistors, field effect transistors, all these things. So integrated circuit consists of a active components and passive components. So passive component means resistors, capacitors, right? Active components means transistors, field effect transistors, diodes. Okay. So integrated circuit consists of active and passive components fabricated together on a single crystal of silicon. So if you see the advantage, so cost is low, so improves the performance, the speed is high, the power consumption is low. So these are the advantages of integrated circuit. So when it comes to classification, here the ICs are classified as monolithic ICs and hybrid circuits. So monolithic circuits and hybrid circuits. Again, monolithic circuits can be divided into bipolar and unipolar. Again, bipolar is divided into PN junction and dielectric isolation. Here the unipolar is divided into MOSFET and JFET. So this is the classification of ICs. Okay. So what are the different types of ICs based on the chip size? Based on the size, we are having different types of ICs. So small scale integration. Small scale integration, it has less than 10 gates. Less than 10 gates or less than 100 components. Okay, it consists of IC means it consists of active and passive components. So if the IC contains less than 10 gates, then it is called small scale integration. If you see the medium scale integration, here the gates per chip is between 10 to 100 and the components will be less than 500. Large scale integration, so the gates per chip is in between 100 to 1000. So that is the large scale integration chip size. So in VLSI, very large scale integration. In VLSI, more than 1000 gates per chip. More than 1000 gates per chip are there in VLSI. In ultra large scale integration, so it contains more than 10,000 gates. It contains more than 10,000 gates, right? So these are the different types of ICs based on their sizes. So small scale integration less than 10 gates, medium scale integration less than 100 gates, and large scale integration between 100 to 1000 gates, very large scale integration between 1000 to some 10,000. In ultra large scale integration it is greater than 10,000 gates per chip, right? So with this I am going to stop the presentation. If you have any doubts, you can ask me. So in the today's class we have discussed about ICs, classification of ICs, level translator, FET differential amplifier, cascaded differential amplifier, and current mirror circuit. Okay, so current mirror circuit. Current mirror means, so here current mirror circuit is used to improve the CMRR. So the output current is equal to the input current. So cascaded differential amplifier, so to improve the higher gains, so to get the higher gains we are using cascaded differential amplifiers. So FET differential amplifier, to get the high input impedances we are using FET differential amplifier. So level translator circuit, so to minimize the DC level to 0 level we are using this level translator circuit. Okay. So in the next session we will discuss what is OP-AMP and what are the characteristics of OP-AMP. So what is the working of OP-AMP and all this. So with this I am going to stop this presentation.